Good afternoon. We are Team Energy, and we will be discussing some different forms of energy that we feel are the most suitable for Mars. My name is Teresa Marina Salva.
My name is Nicole Meyer.
I'm Jack Moripalishina.
And my name is Martin.
So I would like to start with these few questions to think of it to ourselves. So imagine, you woke up tomorrow and the lights simply didn't turn on. No internet, no transport, no cooling. How long do you think that we could function? This is why we are discussing how we can get energy on Mars, as it is one of the most important things for life.
So obviously we have to choose certain energy sources to rely on when we're on Mars. And in fact we had a whole process considering every single energy source. So first we thought of geothermal, as much as this would be possible because Mars's core still has some heat. It is much cooler than Earth, and in fact to obtain a substantial amount of energy you would need to dig even deeper. And this would obviously need energy itself, and it would be really difficult to dig that deep. And we also considered wind turbines, as much as this is possible, and Mars's atmosphere is very light. And so we wouldn't be able to also produce enough energy for the whole colony. There was also the issue of fossil fuels, because in fact you don't have fossil fuels on Mars. Although this could be shipped from Earth to Mars, it wouldn't be reliable since it is in fact finite on Earth, and it would take a lot of money and fuel itself to get to Mars. Also, one that we could not do for sure was tidal power, because we also don't have any water bodies on Mars because all the water is frozen. And so we decided on nuclear power. This is because it is very efficient and it takes long for the fuel to finish. And also as a backup, we decided on solar energy because although Mars is further away from the sun and so there is less sun energy, we can still get better quality material, so then we can get more light energy.
So the colony, for a size of 10,000 people, we calculated around 200 megawatts, and because of the food team, they would need a lot of power. So that would probably be around 1 gigawatt. So we also plan on redundancy, as she said before. So we would have solar panels as a backup. And the goals are a long-term sustainable and reusable power. Obviously, the continuous load is not 200 megawatts, but about 1 gigawatt. There would be some peak loads, which will be smoothed out by the solar panels as well. And the solar panels would be also a backup for life support systems in case of a failure in the power plant or in case of maintenance. So we didn't choose a normal nuclear reactor, we chose a plutonium breeder reactor, which basically uses two types of fuels. First one is uranium-238, which is a highly enriched type of uranium, and plutonium. What it basically does is that it creates new fuel as it's using it. So this would last around 84 years at 200 megawatts. At 800 megawatts, it would last something around 20 years, if you do the calculations. And the reactor would weigh around 200 tons. This could obviously be shipped in different parts. And it also reduces frequency of refueling trips from Earth because obviously it will last a long time. So, as I said before, the reactor converts fertile isotypes such as uranium-238 into plutonium-239, which would be fissile fuel while generating energy. The reaction will be started by the original plutonium-238 to produce heat, and the heat would heat up water, and via the turbines it would produce power. This could also be used as a way to warm up the habitats. So to cool down the reactor, we could use also those. So the reactor would weigh around 200 tons. It's included with the fuel, so the fuel would weigh around 40 tons of that weight. The fuel would be 50% effective. If you look at normal nuclear reactors, it's much less, so around 10 to 20%. This also produces low levels of high-level waste, low amounts of high-level waste, which they're going to talk about in more detail later. And the total energy output over a lifetime will be 147 million megawatts of electric power, and one power plant could produce around 837 megawatts on average. And since food needs a lot of power, we could ship 2 of those, which would bring us well above the 1 gigawatt needed. So this would also be a good idea because since it lasts a long time, it could also predict for further expansions of the colony. So we have some headroom in those regards. These are calculations made on 200 megawatts, so the reactor will be running at full power. If you times it by 4, it would be around 20 years instead of 84. And we could use, as I said before, 2 to 3 reactors. The third reactor, if it's needed, we could use it as a backup for maintenance if solar powers aren't enough, but that would also depend on if we're able to ship it there. One of the ways to deliver the reactor there would be Starship. Obviously, we don't know what kind of technology will be there in 50 years, but we wanted to see something that is present today. For example, Starship has a payload to Mars of around 150 tons, which is 50 tons less than the reactor. So you would need around 2 flights per reactor. This is obviously technology that is available right now. Probably in 50 years there will be much more developed technologies. The advantages for these systems are that there will be minimal launches to bring the reactors there. It's highly reliable since we also have 2 types of powers, the nuclear energy and the solar backup. It has a long operational lifetime, again not 84 but 20 years. Has a high energy density. As I said before, the plutonium and uranium will be around 40 tons, already included in the 200 tons of the reactor. And it's also scalable for future industrial expansion. We were also looking into bringing a mini nuclear reactor that would be switched off most of the times and only used as a further backup in case we need something happens in the main nuclear reactor or we need to do any maintenance on it. There is one that is used by NASA and some rovers on Mars, so it's also being tested. It's not new technology. And some of the challenges would be handling. Then the people in my group will also explain how will we handle and how will we control this reactor there on Mars. Reactor assembly in low gravity, and for the solar panels on Mars would be limited. The efficiency would be limited because of Martian dust storm, and as said before, the sun doesn't have the same power as it does on Earth. For the waste management, she will continue on to explain.
So, as Martin said, the nuclear reactor will not produce a lot of waste, but we would still have to find a way to get rid of this waste since it is in fact has a lot of radiation. And in fact, even though there's a bit of waste, there are four types. There is high-level waste, and this consists of fuel rods and broken pieces of atoms. This is very dangerous because it has a lot of radiation, and so it cannot be left out in the open. You also have plutonium isotopes. So these form once the fuel will be used up a lot of times, and then it turns into certain forms that cannot be used again as fuel. These are also they have some radiation, and so they cannot be kept out in the open. Then you have intermediate level waste. This is not as dangerous as the other waste, but it still has radiation in it, and it consists of reactor parts, pipes, and chemicals. Then you have low level waste, although this could in fact be prevented in the future if, for example, we have robots to take care of the nuclear power plant, because like that would be preventing gloves and protective clothing. And we decided that we will in fact exploit the surrounding environment of Mars, and in fact there are a lot of lava tubes which, as said before, are big holes underground. And so we decided that we're going to get the waste and put it in special containers that can hold them and prevent radiation from escaping, and then we put them underground, and then like that we're going to cover them with the red oil in the soil. And and then the radiation cannot go up to the surface. And then we realized that this waste generates a lot of heat, and this could in fact heat up the water ice in the soil, and so like that we can in fact make use of this and, for example, grow plants on it. So and then like that we can at least make use of the area that we're damaging by putting the waste inside it.
Okay, so I'm going to be talking about how we can use solar power on Mars. So, some of the problems with solar power on Mars. The first one is that Mars gets a lot less sunshine than Earth does. This is because Mars is about 1.5 times farther than the Sun than Earth is, and so it only gets around 44% of the sunlight that Earth does on an average day. Another big problem with Mars is the dust storms. There's many dust storms, very heavy, and sometimes last weeks or even months. The longest can go even 3 or 4 months. These can cover up the solar panels if we do nothing about them, which would limit the amount of power we can get greatly. This is why solar power is not a steady source of energy on Mars, and why we could not use it as our main source of energy. We decided to go for nuclear power instead, but we instead used solar as a backup. So we found 2 ways to use solar energy on Mars. One of them is solar-powered satellites, which I'm going to be discussing, and the other one is solar panels on Mars, which there is to be discussing. So, solar-powered satellites. Basically, there'll be satellites with huge solar arrays of around 500 solar panels each, orbiting around Mars, and the power generated on the solar panels will be converted to electricity and beamed via microwave onto receivers found on Mars. The reason we chose microwave instead of laser is because laser is much more inefficient. When using laser, roughly 75% of the energy is lost when beaming it, while microwave only around 35% is lost, so it is much more efficient. The receivers will then be able to store the energy on batteries for later use. The satellites would have technology which will allow them to track where the receivers are on Mars, so that they can always aim their beam at the receiver to not waste any energy. And there will be roughly 12 receivers around the equator of Mars, so that wherever the satellites are, they would always be in reach of one of the receivers. So this energy, the main use of it would probably be for expeditions around Mars, for vehicles. This could be for mining expeditions, exploration, even for the buses that the technology group mentioned. But in worst case scenarios, if everything goes wrong, this energy could also be used as a backup.
So I will be discussing the solar panels which will be on the surface of Mars. And we decided to do 2 types of solar panels, one in orbit and another set on the surface of Mars. It's because just in case all of the nuclear reactors stop working, hopefully they wouldn't, we would have another transferable of spare energy as a reserve. So these solar panels will be put on stands so that they can rotate 260 degrees, so they can track the sun, and then at night they will flip upside down, so that since they won't be receiving any more solar radiation, they will be flipped down as well, and this will also prevent them from being damaged. They will be coated with an electrostatic film, which will be installed to prevent any sand from the sandstorms from getting stuck on top, because then less solar radiation will be absorbed, resulting in less energy. Now, an important thing to note is that these solar panels will be much better than the solar panels that we see in our houses here, because these will be stronger, so they can absorb more solar radiation from the sun, because Mars is much farther away from Earth, so the strength of the sun rays will be much weaker. So in total there will be around 18,500 solar panels, 2,500 being in orbit and 16,000 being on Mars. The 16,000 being on Mars will be taking up around 1 square kilometer of space. And then these will also form 25.5 megawatts per hour a day of power, 10.5 megawatts an hour in orbit, and 50 megawatts per hour on Mars. Now, all of this energy will be split into 35-65 ratio. 35% will be going straight to the grid, which will then be split up into 8 different substations, which will be scattered across the civilization. Then the other 65% will be in vanadium and lithium-ion batteries. So as the technology team also mentioned earlier, the vanadium batteries will be a resource which will be mined straight from Mars, because batteries are very heavy, so if we can use any resources straight from Mars, it's much easier. So the vanadium batteries will only be used for the solar energy on Mars, as this will be just as the backup energy. Then the lithium-ion batteries will be used for the energy which are from the solar panels in orbit, and the lithium-ion batteries will be used for any rovers or for any forms of transport. A very important fact is that lithium-ion batteries are also being used for the Curiosity rover on Mars currently.
So now I'm going to be talking about how we're going to be making rocket fuel on Mars. So, in fact, we have decided on using methane and oxygen for rocket fuel, but these, you cannot just find them in the atmosphere, so you have to make them in some way. And so we decided on first getting water from, for example, the polar ice caps. And you can get water, and using electrolysis, you can split it into hydrogen and oxygen. And then you can use this hydrogen and react it with carbon dioxide, which is in fact very abundant in Mars' atmosphere. And if you get them both and you put them into a reactor with a catalyst, example nickel, and in very high temperatures, they will have methane and water as byproducts. And then you can store this methane in gas and high pressure tanks, and also when you need it, and then you can use the oxygen which you would have extracted from electrolysis to react it with the methane, which in fact as a byproduct produces a lot of energy that can in fact be used to launch the rockets away from Mars. And so to summarize, we have discussed using nuclear power as our main energy source and solar power as a backup, and we're in fact using methane and oxygen for our rocket fuel. Thank you.